People, hope we're doing well. Let's go ahead and get started on another problem where we're finding the area. This is asking us to find the area inside the curve. And we did one kind of like this in class, except for it was a cosine-based lemniscate. No, but just like, actually, did we do one that was a cosine? Or whatever. It was a little bit different than this. But remember that a lemniscate is important. It has important distinctions for two reasons. One, r is already squared. Okay, so we need to be careful about that when we're setting up our integral. The second thing is that it kind of has a broken interval, right? Because there are certain intervals on which the petals are not formed because this expression on the right hand side of the equation is spitting out negative numbers, and it's causing an error because r squared can't be negative. Okay. And thankfully, this problem has actually already specified our limit of integration. So that's kind of nice. What we want to do is we want to just go ahead and set it up. We need 1/2 the integral from alpha, which is 0, to beta, which is pi over 2, and then r squared, which is 9 sine 2 theta, and then d theta. And that winds up being it. Okay? So what we need to do is we can go ahead and integrate this one by hand. This is actually really easy. We can go ahead, and if we want to, we can basically put a 2 in here in preparation for it being sine u du. Now, if that's the case, I need another 1/2 out in front. That means when I shoot the 9 out in front as well, I'm going to have 9/4 from 0 to pi over 2 of sine 2 theta to d theta. Now when I integrate, that's going to wind up being 9/4 negative cosine of 2 theta from 0 to pi over 2. Okay, well that means it's 9/4 negative cosine of pi, right? Because it's pi over 2 times 2, so I probably should have put that down here somewhere, minus negative cosine of 0. Now, if that's the case, cosine of pi is -1, okay? And -1 negativized is +1. This is so it's -1 minus a -1. So it's 1 plus 1. And therefore, what I get now is 1 plus 1 times 9/4, and that area becomes 9/2. And of course, you know, you could have done it with your calculator. And if we want to, remember that when we're doing a lemniscate, we're going to need to do both petals, or maybe we'll just, get lucky. So this one can be 3 times the square root of sine 2 theta. And let's go ahead and look at the graph. Now, so oh gosh, that actually gave me both. We'll have to, okay, we'll talk about it later. Let's go ahead and go back to the y equals and get rid of the graph of the derivative. So what happens is, so stop. We have that graph right there. And we know that that right there is going to give us that first petal, and it's going to be 0 to 2 pi. Because if I keep going, let's go ahead and graph it again. Pause. Notice that there was a pause in there. That pause is the pi over 2 to pi interval that is giving out negative values for this right here. Okay? But since I know that this part that I'm looking for is actually part of the graph in here, the part of the function, or part of the equation that I put into R1, what I'm going to do is 0.5 times the integral from 0 to pi over 2 of R1, so R1 squared d theta. And it's 4.5, which is, exactly what we got. So let's move on to one that's a little more fun, a little more interesting. So this one is related, of course, to r is equal to sine of 4 theta. just like the one that we did in class that was related to cosine or sine of 3 theta, or cosine of 3 theta. Now, I'm going to go ahead and show you something real quick. Remember I mentioned Wolfram demonstration? These things are awesome. This right here is sine of 4 theta. And what I'm going to do is I'm going to show you what happens when I start adding a d value, okay? Because remember, half of those petals are generated by positive r values, and half of those petals are generated by negative r values. So as I put this into play, no, that's the wrong one. That is 0. It's this one. No. Oh, no, it's this one. Okay. As I'm going to add, so basically this is sine of 4 theta, and I'm going to start adding constants to it. Okay, pause. Do you see the fact that basically what happened is the petals formed by negative values got smaller and smaller and smaller as I was adding more and more and more and more and more, right? Until such time as I got to the point where only the positive petals were there. But of course, if I keep adding constants, I'm going to see the fact that it widens out, okay? And I get to the point where I get 2, and I get the graph that I have on our right here, okay? Now, and I'll go back to that because that's actually kind of fun. So basically what happened is you had an 8 petal rows, 4 of them were negative, but remember sine of 4 theta can only be -1. So if you have a positive 2 here, basically those negative petals have long since gone bye-bye, okay? So let's find the area inside the curve. This is obviously going to be 0 to 2 pi. Now, I'm not going to do this one by hand, though we could. But let's just go ahead and this is 1/2, 0 to 2 pi. And we just add the 2 plus sine 4 theta squared d theta. All right, well, let's go ahead and plug that into our calculator. We have 2 plus sine of 4 theta. And let's go ahead and see the graph just to make sure that it is what we're looking at. Fantastic. Now it's a little bit oblong because I don't have it square. Remember that you can always go in here and square it up, right? Equalize the axes by zoom 5. And now it looks exactly like we have up on our sheet. Okay, let's go to the home screen and let's just do that. But of course, the only thing different about ours is our limits of integration are different. So we'll do it like that and press enter. And what we get is, don't keep us in suspense, 14.137. And if you wanted to do it by hand, what you would wind up getting is you would wind up getting 9 pi over 2 at the very end after doing all of your, changing of the form of the integrand and, integrating and evaluating using the fundamental theorem of calculus and all that sort of fun stuff. You would get 9 pi over 2, which, by the way, is 14.137 approximately. Okay, now we've done several just finding the area. Now we need to find the area that is defined by 2 separate curves, and this winds up being just a little bit more complicated. Some of them are actually easier than others. This one is actually pretty simple, because what I need is the area that is bounded by, that is basically enclosed by this and this. Well, here's the thing. I notice on this one that this area right here is simply defined by the circle, right? So I can find that just, with arithmetic, okay, with a simple geometry formula. But this right here, I need to add this area to it, and this area is basically defined as a portion of this cardioid. Okay, so Just for giggles, let's actually go ahead and find the points of intersection between our circle and our cardioid. And all we really have to do is just plug in. Right? Where is sine equal to 1 plus cosine? Well, we do a little bit, and I don't know how much of this you remember from trig, but some of these actually wind up requiring a couple of things. Now, remember how we took that sum and we changed it by adding a couple of things into a sum and difference formula so that we could transform it back into sine. We could do that here. What we could also do is we could square it. Now, the only danger in squaring this is the fact that just like when you're doing radical equations or anything like that, when you square it, you introduce the possibility of extraneous roots. Okay, so you need to go back and basically double check that which answers actually accord with the scenario that you're trying to investigate. Now, sine squared plus cosine squared is just 1. Okay, and of course that's 1 over here. So if I subtract 1 from both sides, I get negative 2 sine cosine is equal to 0. Now, of course, I can multiply both sides by a negative 1 and turn that back into a plus. And this becomes sine of 2 theta is equal to 0. Now, we know where sine theta is equal to 0, where its angle measurement is 0 plus pi n. That means that our theta, our points of intersection for these, are going to be 0 plus pi over 2n. And that means that theta, for our purposes here, can be 0, can be pi over 2, can be pi, and of course can be 3 pi over 2. Now, remember that I said that there's the introduction of extraneous roots. And that's largely because when I square it, it doesn't know the difference between cosine minus sine and sine minus cosine and a whole bunch of other stuff. It doesn't know the difference between sine minus cosine is equal to 1 and sine minus cosine is equal to negative 1. So I need to go back and check. Now, this point right here is pi over 2. This point right here is at pi. So really our limits of integration are here. Now, I'm not really interested in both of them because I'm simply using the points of intersection to define that. And I didn't really need to do that because they happen to be at an axis. But it's always good. It's always good to practice those skills. What I need now is basically the shaded area is going to be equal to the green plus the pink. Okay, and I hope none of y'all are colorblind, otherwise that's not going to make much sense. The green is this portion over here, that's cardioid specific, and the pink is this area right here, that's the semicircle. Now, of course, the semicircle, really easy, okay? So the pink is going to be easy, but the green is 1/2, and my alpha to beta winds up being pi over 2 to pi. And then I simply have 1 plus cosine theta squared d theta. And then the pink area is, this is a circle of diameter 1, so radius 1/2. So, but it's also half of the circle, so it's pi r squared over 2. So that actually winds up being pi over 8. And if you plug it into your calculator, which I'm going to do because working it out here just really isn't worth the time and the space, you get 0.571. And that is the total shaded area that is enclosed by both the circle and the cardioid. Now, let's do one more before we get to... let's do one more before we call it quits and start a third video. Now, this one asks for the area enclosed by both curves. And that means this area basically inside here, okay? Now, the great thing about this is that those cardioids are the same shape, and one is simply a rotation of the other, and therefore there's a certain amount of symmetry in there. And if there's symmetry, we can go ahead and use that to our advantage. Okay, so let's sort of split that right down the middle. Now, we notice that there is an itty-bitty piece right here that we need to calculate the area of, right? But the majority of it is up here. So let's actually find this point of intersection and that point of intersection, and let's use it to find, and I'm trying to color half of that, but I botched it because it's just so small, right? But basically I want to find this area and then just double it. Okay, so basically doubling it just gets rid of the 1/2 that's out in front. Okay, so the points of intersection, let's go ahead and find them. So points of intersection. That means I need to know when 1 plus sine theta is equal to 1 plus cosine theta. Okay, well, subtract 1 from both sides. And none of this should come as a surprise. Let's divide by cosine. And so you're looking where theta, or a tangent, is equal to 1. And that, of course, is pi over 4 and 3 pi over 4. Now, you can do that because this is pi over 4 and it goes to 3 pi over 4. Or you can start at negative 3 pi over 4 and go to positive pi over 4. It doesn't really matter. So it's either, our limits of integration are either that or they are negative 3 pi over 4 to pi over 4. Does not really matter. So what we want to do is we want to double our area formula, alpha to beta. Let's go ahead and do it, pi over 4 to 3 pi over 4. And basically we're going to do that. Basically you have to pick the right one, okay? So if you're doing it for pi over 4 to 3 pi over 4, you're going to need basically this right here, which is the cosine one, because this is that curve, this is that curve. And so you have to, depending on which one of these you actually pick, you have to pick the right interval of integration. So you have 1 plus cosine theta squared and then d theta. Alternatively, if you had chosen the other limits of integration, you could have done that. You just simply need to be mindful that this right here is along this one that is hugging what we think of as the y-axis, and that means that it is associated with sine, and so it would need to be that. Now, either way, it doesn't really matter. They both come out to 1.884, and that is the area that is shared by both of those curves. Yay! Alrighty. That brings us to the close of video number 2. In video number 3, we'll do one more area problem, and then we will move on to a discussion of arc length. Okay. As always, if you have any questions, please do shoot me an email. Bye.